we are discussing about sparse representation of signal or input data vector, and in the last lecture we have discussed how, given a dictionary, we can obtain sparse representation of a signal using different pursuit algorithms. Particularly, we have discussed about orthogonal matching pursuit algorithms. Today, I will discuss about another problem of sparse representation. Here, we would like to learn the dictionary itself. So, in the previous case, we have considered the dictionary is given, and given the dictionary of say k atoms, we wanted to get a sparse representation given any input signal of dimension n. Now, in this case, the problem is that we would like to learn a dictionary specific to a set of data. So, given a set of data points, here we have considered the symbol x as a set and small xi, which is representing each data vector, n dimensional data vector. Suppose you have capital N number of such data vectors in that set, then what should be a dictionary D of k atoms, so that it would provide best possible sparse representation for each member of the set. Motivation of learning dictionary could be several, there could be several such motivations. In particular, we would like to learn dictionary adaptive to specific classes of signals or data of interest. So, that would make a dictionary suitable for certain applications and would give you relatively better performance compared to any standard fixed dictionary. And these dictionaries are learned from exemplars, and it also ensures that sparse representation properties are ensured using these dictionaries. So, sometimes it may happen that if we use a fixed dictionary, given any input data, sparse representation may not be possible with that set of atoms in that dictionary. But if we can tune the dictionary for a specific classes of data set, then most likely we will be getting a better sparse representation of data. So, this is also another motivation. So, just precisely let us define the problem statement here for this dictionary learning. We consider a data as an n-dimensional vector, and we consider a set X which consists of capital N number of data points, and let us represent it in the matrix form. So, we consider a matrix X where each column represents the data, and each column is of n dimension. And then we are considering there are dictionaries of k atoms, and again each atom is of n dimension, because it has to be the same as the dimension of the data. We would like to have linear combination of these atoms to represent the data, and that linear combination should be sparse, and the coefficients of linear combination is represented by vectors yi's. So, y is also another matrix where each columns of y represents the sparse representation of data x. So, the dimension of y is k dimensional vector, because k dimensional representation of data point in this case, and so the column vector of the matrix y of dimension k. And if you so our problem is that we would like to obtain a sparse y in the k dimensional real space, such that x equals dy. So, this expresses itself the linear combination of dictionary atoms for each data point, and the coefficients of linear combinations, they are coming from the columns of y, or it could be approximate. So, let us consider let us make a dimensional check of this particular fact. That means, we are trying to factorize the input matrix, data matrix X, into two factors. One part should give me a dictionary of k atoms, the other part should give me a dictionary of n sparse representation for n data points. N here is capital N. So, we consider the dimension of X. This is say small n cross capital N. Then dimension of D, this is small n cross capital K. As you can see that n is the size of the column vectors. So, that is why that many rows should be there, that is small n, and capital K is the number of atoms in dictionary D. So, that is why its number of columns should be k columns. Similarly, for X, n should be the size of the row, because n represents the dimension of the data point, and capital N is the number of data points in X. So, number of columns in X is capital N. Similarly, for Y, it should be capital K cross capital N. So, capital K, once again, that is the dimension of sparse representation of data. That means, a few of those elements in that column vector Y should be non-zero, rest of them should be 0. That is the sparsity, that is the interpretation of sparsity. Very few of them should be non-zero, but the dimension could be very large. It could be K could be quite large, it could be quite large from N, and that is the dimension of data, original dimension of data. And then capital N is the number of sparse represented data vectors. So, you can see the multiplication dy means n cross k matrix into k cross n matrix. You get the dimensional matching here, because you get n cross n data matrix. And let us also understand that how this representation is to be interpreted. So, as we are considering that the data vectors x1, x2 to xn, and say the dictionaries are d1, d2 to dk, and then each y1, let me write y1 as say a11, a12 to a1k, and like this. So, if I consider only the first row, if I consider this dictionary, and these are the vectors, these are the atoms, and this is the coefficients. So, x1 vector, and this is y1 vector, but which is represented by this k dimensional vector. So, x1 is represented as sum of a 1 I di and I equal to 1 to k. That is what is x1 is represented, which means we are multiplying each coefficients with this column vector. So, a11 d1, a12 d2 like this, and it goes a1k, this is capital K, a1k dk. Similarly, if I consider x2, there will be another column vector here. So, this column vector provides the coefficients of this sparse representation. So, x2 will be represented as sum of a to I di, where I equals 1 to k. So, this is capital K. So, in this way, for all n vectors, you have one column at y, one column of capital Y, and this is how these vectors are represented, and this is how these linear combinations of each column vector of x is represented by these corresponding matrix multiplications of d and y. So, you can apply various sparsity constraints, as I mentioned that the k dimensional representation of input vector which are given in the matrix Y, now they should be sparse, which means there should be only a few non-zero elements. So, when I have written a representation say x 1, this vector when I am representing by say sum of a 1 I d I equals 1 to k, only few of these coefficients should be non-zero and rest of them should be 0. So, you can apply various sparsity constraints there. So, one of the so some of these examples of these constraints can be shown here. Say the zeroth norm of y, zeroth norm means number of non-zero element of y, and that should be minimum. You should have that representation, that your representation of dictionary atoms and also the sparse representation would be such that the number of non-zero elements of the each sparse represented vector, that number should be kept as minimum. So, if I consider the whole set Y, all the set Y, we can count how many number of non-zero elements are there in that matrix. That can be also considered as a measure, and we would like to minimize it. Or we can consider that the approximation, that means this is for exact reconstruction x equal to d I, we can consider this, or it may be approximate reconstruction, that it could be, you may not get exact reconstruction of all the input vectors. There could be a tolerance of epsilon in the reconstruction in the sense of L2 norm, and there also we would like to minimize the zeroth norm of the y vectors. We will discuss a particular type of dictionary forming algorithm, which is called K-SVD or K singular value decomposition, and in this case it is the same problem statement. As you can see, it is given a set of training signals to obtain the dictionary of k elements that leads to the best possible representations for each member in this set with strict sparsity constraints. Now, the sparsity constraints here we have mentioned. With this I would like to add, in this case instead of considering always minimization, we can make a bound that the zeroth norm, it should be less than or equals some constant t naught, which is a small number, and we would like to minimize the L2 norm in this case, that we will by keeping this constraint we would like to minimize the L2 norm of the reconstruction. So, the principle of this algorithm K singular value decomposition or K-SVD, that is how this algorithm is popularly known. It generalizes the k-means clustering algorithm or k-means clustering problem rather, and we know that in k-means clustering what we get representatives of k groups of data vectors, and each representative acts like an atom in this case context, and then you get an extreme sparse representation if I consider the any member of that group is represented by that atom only. So, we will see that in terms of Y matrix how this vector looks when we consider it's an extreme sparse representation. So, in the case of and in K-SVD, instead of only a single atom representation of k-means clustering, we consider a sparse linear combination of k atoms. So, what it does, it chooses a dictionary of k atoms and then it obtains a sparse representation, and then it updates dictionary atoms to get a better representation out of this. and repeat steps 2 and 3 till convergence. So, once it obtains a sparse representation using these atoms, then it checks whether any sparser representation is possible by updating some of these dictionary atoms and also with better approximation of the input signals. And if it is possible, then it updates and it repeats this process till there is no such improvement is possible. So, let me once again revisit, let us revisit this K-means clustering algorithm, and in the context of this particular discussion. Say we have a set of atoms which forms a dictionary. You remember that we have to initialize the centers of clusters, K centers of clusters. Now, those centers are considered here as atoms of dictionary, and then what we do that we assign the training examples to their nearest neighbor in the dictionary D. So, that is what we did in K-means, and then given the assignment, then we update D to better fit the examples. So, for K-means clustering, we have used L2 norm to check to compute the distance between any sample vector to the dictionary, to the atoms or to the center of clusters, and then whichever is nearest, we assign that vector, input vector, to that cluster. And once the assignment is over, then you have once again K partitions, then again recompute the centers. So, that is what the updation process. So, you update mean of each partition of assignment. We started with any initial set of distinct atoms, and then after convergence you consider those are the learned dictionary atoms. So, your code book here is the K cluster centers, those are the dictionary atoms, that is your code book, and you have these training examples, and this is what is the representation extreme sparse sparse vector. You can say jth vector representation would be in this form. All the elements would be 0 except 1. So, the 1 denotes that atom which is assigned to that input vector, or this input vector belongs to that group where this atom is the center of that cluster. So, that is what that is why it is called extreme sparse, because it has only one non-zero element and rest of them are 0. So, in your sparse representation you have only this type of vectors, that means extreme sparse vectors. It should be one of them, and your optimization problem, as we have considered for K-means, it is once again, as you can see, you are minimizing the L2 norm, square of the L2 norm, and your update policy is that if ith input vector is closest to the dictionary atom, rth dictionary atom, then assign the rth sparse vector, rth then the representation should be ER, which is extreme sparse vector, which means then non-zero element 1 would be only at the rth location. So, once you have computed that location, then for all the vectors, once the assignment is over, then you update each partitions, which means that you are considering mean of those input vectors which have the same assignment. For example, with the same assignment of EJ, that is the sparse vector representation for the jth group, and you compute its mean, that would be your new dictionary, updated dictionary atom. So, this operation you are doing iteratively, and at the when it converges, then you stop, and that is the dictionary you learned, and already the sparse representations are also derived as extreme sparse vectors for each input vector. So, we have mentioned this is Frobenius norm that we should consider. So, that was K-means clustering, and let us consider now that how this concept is generalized for K singular value decomposition approach or K-SVD algorithm. In this case also we start with any initial code book. We will discuss how this code book is derived here, and suppose there is a initial code book, and also you have the training examples as given in this form. It is a capital N number of data points, and it can be represented as a data matrix X, and you would like to get sparse representation, once again a matrix of K cross N. Each column represents the sparse representation of a data vector, and yi provides linear combination of maximum T naught to non-zero terms that I mentioned while discussing the sparsity constraint that is involved in K-SVD algorithm. So, the optimization problem here is that we would like to minimize the, once again the Frobenius norm x minus dy, it is a generalization of L2 norm, square of the L2 norm, and subject to that number of non-zero elements for each sparse representation is less or equal to T naught. So, this computation is carried out by a nice manipulation of the optimization function that we will discuss here. If I consider my optimization function, if you note here, the optimization function is given this, that means Frobenius norm of x minus dy, and how this can be written in a different form, that we would like to discuss. Now, consider the jth row of y. So, if you remember the representation of y, each column is a sparse representation. So, I have represented by the coefficients a11, a12 to say a1k. So, this is the y1 of the sparse represented vector, and this is representing x1. So, y1 is representing x1. Similarly, y2 can be represented as linear combinations a21, a22. So, this is my say notation a2k. So, this is y2, and in this way you are representing say any particular small k y as say ak1, ak2 to a k, one is small k and it is capital K is the dimension, and finally, there are n number of representations because there are n number of data points. Now, you consider any particular row, say jth row, which means this should be a1j, a2j, a small k j, a capital N j. So, this j is represented as this jth row vector. So, now this expression x minus dy, this can be conveniently written in this form. You can see that what it is doing, it is the sum of the rank 1 matrices in the other way. So, you have, if I write it in this way, that d1, d2 to dn, and this is the y matrix. So, we can write it as say d1 into this first row, that means y 1 t in our notation. So, d1 this into this. So, the dimension of d1 is n cross 1 and y 1 t, its dimension is 1 cross n, because there are n elements. So, there are n elements in a row, there are n columns. So, and only one. So, this would give you a matrix of n cross n, and X is a matrix which is of n cross n. So, if I consider sum of all these matrices, that would actually cover the X. So, it is the same. So, this dy is the same as this one. It is not same, it is trying to represent that. We are trying to get that d and y which will be the same as x if I multiply them, but dy is equal to sum of dj and y tj, where j equal to 1 to k. So, this is the trick. So, you are considering every atom dj and finds out what is its contribution to the reconstruction of dy, the whole multiplied factor. So, the advantage here is that if you do that, then what you can consider, you can separate out the contribution of a single atom, say dk. So, this is the single atom dk, this is the contribution of atom dk, and this is the contribution of rest of the atoms towards formation of dy, and which we would like to get as close as possible to x. So, if we have this, then then the idea is that since we are separate it out, so we can observe just what is the effect of a single atom. So, if I keep all other thing constant, then what is the best dk and y tk that should approximate this particular factor. Let me call it as say E. So, we can compute it because everything is given in your in your hand at this stage. You have the input data vectors, you have the set of atoms, that is the, say suppose you are doing iteratively. So, k minus 1 its set of atoms, you have also the sparse representation in the previous k minus 1 its sparse representation. So, you can find out what is the value of this. This is the error of approximation using except kth atom, this is error of approximation. So, this so the error can be this minus this. So, if I can update dk and ytk such that it is close to E, then my error would be minimized. So, that is the idea, and that is what this algorithm does, that keeping other terms fixed. So, it gets Ek. So, to do that, what we can do, we can perform the SVD of Ek. So, this is I am mentioning as Ek, and this is what is written. So, let me rub my writing. So, if I perform SVD of Ek, and then you know that with singular value decomposition you get set of orthonormal column vectors of u and v, and consider the columns of u, the first column of u with the maximum singular value and column of b of the same maximum singular value. So, you take the column of u and you can normalize it, that is what is your dk, and then maximum singular value into the column of v will give you the yk tk, that representation. That could be one possible close approximation. It is not exactly equal to Ek, it is the best approximation of rank 1 approximation from the theory of approximation of matrix using this kind of singular value decompositions. Now, this is one best representation. Problem here is that here you are not ensuring that ytk or that coefficients would be sparse. So, this is a problem that, so as I mentioned, we can consider first column of u as dk, and the first column of b multiply it with the singular value d11, which is the maximum singular value as ytk, but the column vector, this column vector may not be sparse. So, what we should do in that case? So, this is a trick that we can enforce sparsity by considering only those samples of the input which has non-zero contributions towards decay. That means, they have non-zero coefficients. So, choose only samples from x which have a non-zero component along decay, and from there you can reduce the error matrix Ek to EKR. So, you are only considering those input samples related to that only, and from there you can rewrite the equations and you can get EKR, you can get the reduced representation of the row YRK, and that you can use the once again singular value decomposition of EKR and then update DK and YTK from there. So, you can repeat for all DJs and obtain the updated D and Y in this form, and you should repeat these things till convergence. Actually, convergence like k-means clustering, here also the problem here that it can get local, it can stuck at a local optimum point in this case. So, performing SVD, since you are performing this singular value decomposition k times for k atoms in each iteration, we call this algorithm as K-SVD. So, finally, if we like to give the overview of this algorithm from the total perspective, that your input is x data points, sorry, n capital N data points and represented by the set x, or which can be also represented by a data matrix x, and your output is your k number of atoms of the dictionary D and also the sparse representation of each input sample y. So, the first step is that you have to form an initial dictionary of k atoms, and that any method you can use, k-means clustering can be also used. Then obtain an initial sparse representation y using any pursuit algorithm. So, you can use k-means clustering for that, or you can use orthogonal matching pursuit for this sparse representation. Then you iterate for updating jth atom and sparse representation associated with this atom, and you go on doing these iterations till there is a convergence. So, there are some applications of the K-SVD algorithms. I mean, it can be applied for data compression. There are various image processing operations where denoising is applied. Actually, the idea here is that since once again you have factorized the input data, you only retain those factors which are important, and where the coefficients are negligible, then you can reject it. By doing these things, you can compress data, you can denoise data, you can deblur data. The other applications, other kind of computation could be, you can learn dictionaries of different levels of representation of a signal. For example, high level representation, low level representations, and then if you establish the mapping between two dictionaries, that itself can give you an algorithms for increasing the resolution of signal. So, super resolution is that task which is called. So, mapping of learned dictionaries can be used in this case. In painting also another task of image processing, where you take out some area and you fill that area by looking at the content of the image seemingly, so that the discontinuities of extraction of the object from that image is not felt by a viewer. So, there also this kind of dictionary learning and mapping could be used. So, let me summarize the topics what we discussed under the title of dimension reduction and sparse representation. So, in dimension reduction, we discussed about the technique of principal component analysis and also a technique Fisher's linear discriminant with respect to classification task. So, for principal component analysis, the objective was to represent data in a minimal subspace, and it involves, we have seen it involves coordinate transformation. It chooses a direction maximizing variance of dominance component, and it decorrelates data across different dimensions. Whereas, in Fisher's linear discriminant, the task was to project the data in a 1D subspace and then use it for classification, and this projection itself gives you a linear discriminant function. And in sparse representation, we have discussed about different pursuit algorithms like matching pursuit, then orthogonal matching pursuit, then basis pursuit. We have given just the problem statement, but we did not discuss the algorithmic steps. And then we also discussed a technique for dictionary learning and using it how to derive sparse representation. In particular, we discussed about this algorithm K-SVD. So, with this, let me stop, and this is the end of this particular topic. We will start a new topic in my next lecture. Thank you very much.